In the context of interval estimation or confidence intervals more broadly, we can sort of flip the problem that we're normally dealing with around and think about, instead of trying to find a confidence interval, we can take an interval estimator and then ask, well, what is the coverage probability of this interval? And when we're thinking about coverage probability, what we're really thinking about is, well, what is the probability that the true parameter value is going to fall within the interval that is given by the interval estimator we're thinking about? So if we follow this process, what is the probability that the intervals we come up with are actually going to contain the truth? So given a specific interval estimator, we can use the sampling distribution in order to compute our theoretical coverage probability. And so when we start talking about the coverage probability, we're really thinking about this as a theoretical quantity, right? And it's going to be the theoretical probability that a specific interval contains the true value. Okay? So in order to sort of formally define this, we can think about having some interval. And we'll talk about this around the mean, but the same ideas are going to apply around any estimator. So let's say that we have this interval around the mean, and just for sake of example, we're going to take this interval to be x minus a to x plus b, right? And so here, a and b are going to be some values, either constant values or values that you could compute based on the sample. Right? Now, if we're going to assume that this is normally distributed, then we're going to be able to use the normal distribution to calculate probabilities around this interval. Right? And so either we'll think about this as being normally distributed, or we can think about this as coming from a very large sample, and as a result, we can use the central limit theorem or similar results in order to apply the normal distribution. Now we can take this interval that we've outlined here, so x bar minus a to x bar plus b, and we can treat that as a confidence interval. And then if we're treating this as a confidence interval, because we haven't formed it through one of the usual procedures to form confidence intervals, we don't actually know what is the confidence level for that interval. What is the coverage probability? How likely is it that mu is going to fall in this interval? And so because of that, we say that there's this unknown coverage probability, or this unknown confidence level. Now we can actually go ahead and try to determine this based on the sampling distribution, right? And so what would we be thinking about in this context? Well, remember that a confidence level for a confidence interval is defined based on how likely it is that the true parameter value falls within an interval. And so in this case, what we're thinking about is we want mu to be within the interval, and our interval is x bar minus a up to x bar plus b. Okay. In this interval, the randomness is all coming from the fact that x bar here is random, right? And so what we're really thinking about here is we want the probability that mu is going to be greater than or equal to x bar minus a, and at the same time, we want mu to be less than or equal to x bar plus b. And we can write this out as this joint probability here, where now what we're really emphasizing is that the randomness comes from x bar, and so this becomes a little bit easier to think about as being the probability that mu plus a, where we're sort of just moving that a over to the other side, is greater than or equal to x bar, and then on this one we get mu minus b is less than or equal to x bar, right? And we can sort of write this out in one single statement here, where we think about mu minus b is the lower bound, right? So that's mu minus b less than or equal to x bar less than or equal to mu plus a, right? And so this interval is going to happen with this probability here. And this probability here, because we're assuming that x bar follows a normal distribution with, say, a mean of mu and a variance of sigma squared divided by n, because of that, we can actually work out probabilities associated with this statement here using our normal probability calculations. Right. And so if we actually sort of start walking through this here, right, what we see is that we can follow through this same sort of procedure. So we want x bar minus a to be less than mu, which is less than x bar plus b, right? We can write this out in that joint probability we were just looking at there, which then, once you rearrange, ends up being isolated for x bar alone, right? Now, in this, moving from these two steps here, what we've actually done is we have standardized as well, right? And so what you would have actually found, or what we had written down previously, was we had that we wanted mu minus b less than or equal to x bar less than or equal to mu plus a. And so if we want to standardize this probability, we're going to subtract mu and then divide by sigma over the square root of n. And so then we get mu minus b minus mu over sigma divided by the square root of n less than or equal to x bar minus mu over sigma over root n less than or equal to, and then mu plus a minus mu sigma over square root of n, right? And so then in this case, we're going to have mu and negative mu cancel out, mu and negative mu are going to cancel out, and that's going to give us this expression that we have on the screen here, right? And so that's sort of the missing step there. But then once we're here, right, this is going to become the standard normal probability here, right? So this should actually be the standardized version, and in here, we should actually be writing that this is a z here now, okay? So once we have that as a z there, then this becomes phi minus phi, right? And so that's our normal probability calculation here. And so as a result, even though we sort of formed an arbitrary interval here, then we can actually calculate this probability. And we could do the same thing for other intervals that weren't just x bar minus a and x bar plus b, right? Using the same types of procedures. And so we can take a look at an example of doing that now. Here, what we're dealing with is we have education researchers, and they're interested in estimating the proportion of individuals, right? So we're dealing with a proportion rather than a mean, who experience test anxiety when faced with a large final exam. And so what they want to do is they're going to take the proportion of individuals in the sample who report test anxiety, and then they're just going to add plus or minus 5% of individuals, right? Plus or minus 0.05. And so the total interval is going to be given by p hat plus or minus 0.05. Now, why are they doing this? Who knows, right? Maybe 5% seems like a good sort of margin of error that they're dealing with. But they're going to do this, and they're going to take samples of size 225. And our question to answer here is, in terms of the worst case scenario, what is the coverage probability of this interval? And so in other words, what is the probability that the true proportion is going to fall into our interval here? And so if we write out what we're sort of hoping to happen, right, the lower bound is going to be p hat minus 0.05, and we want that to be less than or equal to p, which is less than or equal to p hat plus 0.05. And because we're dealing with a large population here, what we can say is that p hat is going to be approximately normally distributed, right? And the mean of it is going to be p, and the variance of it is going to be p 1 minus p over n. This follows from the normal approximation to the binomial distribution, right? And so using these sort of intervals here, we can follow a very similar procedure to what we were working on the last slide with the mean, and actually work out this probability for the proportion here, right? And so if we actually start rearranging, then what we should find is that p hat needs to be less than or equal to p plus 0.05, and we also need p hat to be greater than or equal to p minus 0.05. And so then writing that out in total gives us p minus 0.05 less than or equal to p hat less than or equal to p plus 0.05. And we want the probability of this statement here, right? That's the probability we're ultimately looking for. We can standardize here. So this is going to be the probability of p minus 0.05. And then we subtract off the population mean over here from the sampling distribution. Divide that by the standard deviation, so that's the square root of p 1 minus p over n less than or equal to, and then we have our p hat minus p divided by the square root of p 1 minus p over n less than or equal to, and then we have the upper bound here, right? Same thing, applying this across the board. Right, and so this is the general procedure we're thinking about here. And the piece to note is that in our case, we actually are looking for the worst case scenario probability here, right? So we want the worst case scenario. And when we're dealing with a proportion, the worst case scenario is always going to come by taking p equals to 0.05 for our variance term, right? So for the term down here, in these terms, we want p equals to 0.5, right? So with that, we're going to have the largest possible variance. And so then at that point, filling in p equals 0.5 for this, filling in n is equal to 225, and then noting that the p and the minus p are going to be canceling out here, we're going to be left with some normal probability calculations, right? Where this is going to be z in the middle, okay? And so we can walk through that whole probability calculation here, okay? So we get that in general, p hat is going to follow this normal distribution with the mean of p and a variance of p times 1 minus p over n, as long as n is large enough, and 225 is probably big enough. The variance is upper bounded whenever we take p is equal to 0.5, right? So that's our worst case scenario there. And then we can walk through this same probability calculation that we were doing, but here just the values of 0.5 and 225 are actually filled in, and working through that, we get phi of 1.5 minus phi of negative 1.5, right? Once we're at this point, we can turn to statistical software to actually express this in a numeric way, right? And so if we use R, we plug in p norm 1.5 minus p norm of negative 1.5, that's going to give us 0.8664. And so what we're saying here is that judging by this interval where you add and subtract 0.05 to the proportion, in the worst case scenario, that's going to have a coverage of 86.64%. And so if you were following this procedure, you could say that this procedure is going to give you an 86.64% confidence interval whenever n is equal to 225. Right? And so in a sense, we started, rather than trying to come up with an 86.64% confidence interval, we started with the interval estimator, and then we worked out what is the coverage probability there. Now, when we're talking about coverage probabilities, it's actually important for us to sort of make a distinction between coverage probabilities and confidence levels. Okay, so the coverage probability is meant to give the true theoretical probability that the interval contains the true parameter, right? It's this theoretical calculation, and it's going to be based on the true sampling distribution. This does not always equal the confidence level. So if we think about it, the confidence level is sort of a promise of the coverage, and it's going to oftentimes be sort of approximate rather than exact, right? And so oftentimes we're using the central limit theorem to approximate the sampling distribution, and we use that to come up with the confidence level. The coverage probability is always supposed to be computed based on the true theory. And so in that past example, we were actually thinking about not the coverage probability very specifically, we were thinking about sort of the worst case coverage probability or the approximate coverage probability. Right? In order to have correctly computed the coverage probability, we would have actually needed to use binomial distributions directly. And very often we're going to sort of use coverage probability and confidence level interchangeably, right? But importantly, these are actually two distinct concepts. The coverage probability is the true theoretical probability that the truth lies within the interval, and the confidence level is sort of the approach that you're actually saying. You're actually giving some level of confidence with it. And ideally, those two are exactly the same. In a perfect world, those are exactly the same. But sometimes, because of approximations, your confidence level, you're going to say this is a 95% confidence level, but there might actually only be 90% coverage probability, or there might be 99% coverage probability, right? So those things can actually become misaligned whenever you're using approximations. But if you have an exact confidence interval, then those two things are going to be exactly equal to one another, right? So the approximate coverage probability that we calculated is actually giving sort of that confidence level of the interval rather than the true theoretical coverage probability. Again, in a perfect world, our confidence level and our coverage probability are going to match, but just remember, the coverage probability is this theoretical concept that's based on the true sampling distribution. The confidence level is based on sort of the nominal distribution that we're actually using. We're actually going out and applying this, and it might not be exact. Sometimes we might have under coverage, sometimes we might have over coverage, but hopefully it's going to be approximately the same thing. Right? And when we are sort of willing to work with the sampling distribution, or when the sampling distribution is known, we can either be presented with an interval and work out what is the coverage, or we can decide we want some set coverage, we want some confidence, and then work forward to figure out what the interval estimator needs to be. Okay, so given some interval estimator and a true null distribution, then we can use that to determine the theoretical coverage probability. The theoretical coverage probability may or may not match the confidence level, but we really do hope that those two things are going to be aligned. And when you're thinking about trying to do these calculations for yourself, really what you're looking for is that approximate coverage probability or the confidence level directly. And that's going to be something that you can sort of always work out on the basis of whatever interval estimator you're actually looking at, plus the null distribution or the approximate sampling distribution.